Let's say we have a first order differential equation and we're trying to solve for y as a function of t. And if our equation can be expressed as some two variable continuous function of t and y, and let's call it m of t and y, plus another continuous function n of t and y times the derivative of y with respect to t, all that is equal to 0. And let's say that there is some special function out there, and let's call it u of t and y. And when you take its partial derivative with respect to t, you get this function m of t and y from the equation. And when you take its partial derivative with respect to y, you get the other function in the equation n of t and y. And so if there is such a function out there that satisfies this condition, then that equation can be considered the exact differential equation. So then we can say that the equation is the partial derivative of u with respect to t plus the partial derivative of u with respect to y times the derivative of y with respect to t is equal to 0. And if you've taken multivariable calculus or calculus 3, then you may recognize the left side of this equation as the ordinary derivative with respect to t of the function u of t and y, because y is a function of t, and that will be equal to 0. And if the ordinary derivative of something is 0, then we know that that something has to be a constant. So that tells us that the special function u of t and y has to be a constant. So if we can find this function, then we have found the implicit solution for our equation. So if we suspect that the equation that we're trying to solve is an exact differential equation, before we try to find the special function, we must first figure out if it even exists. And if we start off assuming that this function does exist and that it's continuous, then we know that its partial derivatives of the first order are also continuous, which means that the partial derivative with respect to y of the partial derivative of u with respect to t is equal to the partial derivative with respect to t of the partial derivative of u with respect to y. And we know that the partial derivatives of u are the two functions m of t and y and n of t and y. So that means the only way that this function u can exist is if the partial derivative of m with respect to y is equal to the partial derivative of the function n with respect to t. And if that's the case, then you know for sure the equation you have is an exact differential equation and that this special function exists. So to show the process of solving an exact differential equation, let's work on this initial value problem. So if you have an equation that you suspect is an exact differential equation, the first thing you need to do is make sure that it's in the correct initial form. And we said that that form is some two variable function of t and y that we called m of t and y plus, and it's important that it is a plus another function that we call n of t and y times the derivative of y with respect to t, and all of that has to equal 0. And so if we look at our equation, it looks like it already is in that form. So we can call this m and we can call this part n. So that means m of t and y is 2ty minus 9t squared. And we can say that n of t and y is equal to 2y plus t squared plus 1. If you have your equation in the correct form, the next thing you need to do is a quick test to see if it's an exact differential equation. And remember that we said if the equation is an exact differential equation, then there has to be some special function that we called u of t, such that its derivative with respect to t is the function m in the equation, and its partial derivative with respect to y is the function n. So that means if this equation is exact, then the derivative of m with respect to y would be equal to the derivative of n with respect to t. And that is the quickest way you can find out if the equation you're trying to solve is an exact differential equation. So in our case, it would mean taking the partial derivative with respect to y of this function, and then comparing it with taking the partial derivative with respect to t of this function. And if they're equal, then it's an exact equation that we're working on. And when we take the partial derivative of m with respect to y, we get 2t. And we also get 2t when we take the partial derivative of n with respect to t. So there you go. The equation we're working on is an exact equation. So now we know that the function u exists and that its partial derivatives are the function m of t and y and n of t and y. So to find the function u, we can integrate either m or n, and let's go ahead and choose m. So we can say that the function u of t and y is equal to the integral of the function m of t and y with respect to t. Now if we chose the function n, then we would have to integrate with respect to y. And so in our case, the integral of m of t and y is the integral of 2ty minus 9t squared dt. And when we integrate that, we get t squared y minus 3t cubed plus, now instead of a constant of integration, what we will put here is actually a function of y. And the reason why we're doing this is because we're taking the integral of the partial derivative with respect to t of u. So that means when u was differentiated with respect to t, all of the constants and the terms that contained y differentiated away to 0. So to account for that, we're using h of y instead of just a constant. So now that we have most of our function u of t and y, then the next thing we need to do is figure out what this h of y is. And to do that, what we can do is we can take the derivative of u with respect to y and then set it equal to the function n, because we know that's the partial derivative of u with respect to y. And after that, we can solve for the function h of y. So when we take the derivative of u with respect to y, we get t squared plus the derivative of h with respect to y. And we will make that equal to the function n, which is 2y plus t squared plus 1. And now we solve for h. So when we subtract t squared from both sides, they cancel out, and we're left with h prime of y is equal to 2y plus 1. And so to get rid of this derivative, we integrate both sides with respect to y. and that becomes h of y. H of y is equal to y squared plus y. And we don't need to include the constant of integration here because it will just be absorbed into another constant when we plug this back into the function u. And so next, all you need to do is just plug h of y back into u. And so when you do that, we get u of t and y is equal to t squared times y minus 3t cubed plus y squared plus y. And remember that this function u is actually a constant, so all that can be equal to some constant. And this actually is the implicit general solution for our equation. So now we have our special function u, and we said that it's a constant. And the reason why we know this function is a constant is because the original equation can be expressed as the partial derivative of u with respect to t plus the partial derivative of u with respect to y times the derivative of y with respect to t. And all of that will be equal to 0, which is the same thing as saying the ordinary derivative with respect to t of the function u of t and y, which is also a function of t. And we're saying that that is equal to 0. And when the ordinary derivative of something is equal to 0, then we know that that something has to be a constant. In this case, that something is the function u. And so we can actually rearrange this function, and we can say that u of t and y is equal to y squared plus y plus t squared times y minus 3t cubed. We said that that is equal to the constant c. And we can factor out y from here, and we can say that it's equal to y squared plus t squared plus 1 times y minus 3t cubed is equal to c. And the reason why we rearranged it this way is because if we have it in the quadratic form in terms of y, then it will be easy for us to solve for the explicit solution later. So at this point, we can actually plug in the values of the initial condition to solve for this unknown constant c. And so when we do that, we get u of 0 and negative 3 is equal to negative 3 squared plus 0 squared plus 1 times negative 3 minus 3 times 0 cubed is equal to c. And this cancels out. This just becomes 1. So the unknown constant c is 9 minus 3, which is 6. So the unknown constant of the particular solution that satisfies this initial condition is 6. And so we can plug this back into the function u and solve for the explicit particular solution. And so when we do that, we get y squared plus t squared plus 1 times y minus 3t cubed is equal to 6. And we can subtract 6 from both sides, so we can make this quadratic equation equal to 0. So when we do that, we get y squared plus t squared plus 1 times y minus 3t cubed minus 6 is equal to 0. So now this is a quadratic equation for which we can use the formula to solve for the function y. So we're saying that this right here is the coefficient of y, and this would be the constant term in our quadratic equation. And so the formula for the quadratic equation is negative b plus or minus the square root of b squared minus 4ac over 2a. And we're saying that b is this term right here, and the constant c is this term right here. And so when we plug the equation into the formula, we get y of t is equal to negative t squared plus 1 plus or minus the square root of t squared plus 1 squared minus 4 times negative 3t cubed minus 6 over 2, which can be further simplified to y of t is equal to negative t squared plus 1 plus or minus the square root of t to the fourth plus 12t cubed plus 2t squared plus 25. And all of that will be over 2. Now, because we have this plus or minus, to figure out which one is the correct one that we need for our particular solution, we will plug back in the values of our initial condition, and that will tell us which sign is the correct one for our particular solution. And the initial condition told us that when t was 0, then y was negative 3. So when we plug that in, we get negative 1 plus or minus the square root of 25 over 2, which is equal to negative 1 plus or minus 5 over 2. So if we say that the sign is a plus, then it would be negative 1 plus 5 over 2, which would be equal to 2. But if we said that it's negative 1 minus 5 then over 2, then that would be negative 6 over 2, which is negative 3. So that tells us that the sign that we need is a minus sign. And so the final solution, the particular solution of this equation would be y of t is equal to negative t squared plus 1 minus the square root of t to the fourth plus 12t cubed plus 2t squared plus 25, all of that over 2. And this is the particular solution that satisfies the initial condition of our problem.